Hello, this is Brian McKeener, and this is my Lab 5 Choose Your Own Adventure. For this lab, I chose to analyze the motion of a ball dropped from a height as it bounces up and down. In class, we mainly discussed elastic collisions, but for this lab, I am looking at an inelastic collision in the real world. My video will cover an introduction to the topic in my lab, a look at the physics principles used, the code that I created, and a discussion of the results. Perfectly elastic collisions are something that do not occur very often in real life, and because more often they are inelastic. And perfectly elastic collision means that all of the energy is conserved in the model, and all the kinetic energy it has before is equal to the kinetic energy that it has after, whereas an inelastic collision sees all of that kinetic energy transferred to something else. For a ball being dropped from a height, a perfectly elastic collision would see the ball returning to its original height from which it was dropped. In the real world, energy is lost with each subsequent bounce until the ball comes to rest. To describe what is happening to the motion, the term called the coefficient of restitution is used. It describes the ratio of the relative speeds after and before a collision takes place. It can be found by using that ratio or finding the square root of the bounce height over the initial drop height. A coefficient of restitution of 0 means that the collision is perfectly inelastic, while a coefficient of 1 means that it is perfectly elastic. For this lab, the coefficient of restitution that I found was 0.68, meaning that it tends to be a more elastic collision. The physics principles that were used in this lab were mainly Newton's second law to find the final velocity and the new velocities in the new position as the ball bounces. Now we used F equals ma to determine the force on the ball. We ignored drag and friction, and therefore the only force acting on it would be gravity, and so force is equal to ma, where a is equal to gravity, and g, the gravitational constant, is equal to 9.8 meters per second squared. This is the video that I used. As you can see, I dropped a ping pong ball from a height of 1 meter and watched as it bounced up and down a few times. Wasn't able to go completely to rest because the video had poor quality frames towards the end that Tracker recommended that I exclude from my analysis so that as to not skew anything else. From this video, I was able to obtain time and a y values and put that into a CSV file in order to be analyzed in my code in Tracker, which is here. As you can see, I had to set the ball mass, the initial ball position and velocity, and I included in here the coefficient of restitution, delta t, and g. Scroll down, I have in the while loop goes through and does all the Newton's second law business of calculating the new velocity and position, and then this if loop, which will reverse the direction of the velocity as it or with every subsequent bounce whenever the position is less than 1 and the velocity is equal to 0, which is the moment that it hits the ground. It accounts for all that. So go ahead and run the module, and as you can see, pretty quick, but you get that type of path where there's a little bit less than half, which is what you would expect for a coefficient of restitution of about 0.68. As you can see, this looks very similar to the graph of the y motion that is obtained in Tracker. It's a little skewed because the axes are a little bit different. I wasn't able to model every single bounce within VPython because of, like I said, the frames at the end. So again, in conclusion, it was found that the coefficient of restitution for this ball was about 0.68. The model that I created was a pretty decent representation of the motion of that ball, and because of the coefficient of restitution being nearer to 1, it is a more elastic collision as opposed to an inelastic. So my initial guess at it being more inelastic was a little bit wrong, but at the same time is still not perfectly elastic. Thank you for listening.